Hello all, welcome to my course Methods of Adhesion Measurement Theory and Practice. My name is Professor Animangshu Ghatak and I belong to the Department of Chemical Engineering, IIT Kanpur. So, this is our first lecture. So, today I am going to cover the course policy, a little bit of description of the course, a brief introduction of the course content and introduction to strain. So, adhesives come to us in many different forms, structural, solvent based, pressure sensitive adhesives. We are all familiar with that from our very childhood, and there are adhesives which are water based, which are liquid, or like this we all know about this Fevicol, and then there are adhesive tapes. We also come across adhesives in the form of this medical tape, skin adhesive and all that. So, among these different kinds of adhesives, there is one kind of adhesive that is known as this pressure sensitive adhesive. As is pressure sensitive means that you have a thin layer of glue on a tape like the one over here, and then you press it on a surface and it sticks. So, in this particular course we will discuss a lot about this pressure sensitive adhesives, and as pressure sensitive adhesive is in fact it is very large, and in this particular course we will discuss not much about how to synthesize these adhesives, but that how these adhesives work and what are the mechanics of this mechanism of this adhesion. So, this pressure sensitive adhesives we see as this post-it that you must have seen earlier, then skin adhesive, and then this particular adhesive tapes, and the mechanism by which these different adhesives adhere to different adherents also can be found in some other contexts. For example, this gecko as a house lizard, okay, that walks up on a wall. So, they also use then adhesive, so pressure sensitive adhesive. One has made this kind of gecko inspired adhesive. Then there are robotic grippers where also the mechanism is essentially that of a pressure sensitive adhesive. So, pressure sensitive adhesives are very useful, and in this course we will know that how what are the different physics that goes on this adhesion, how can we increase the adhesion than what it would have been if it is only the surface forces of adhesion. So, these pressure sensitive adhesives are mostly soft materials or soft glue, and so the modulus of these materials will be less than about less than 10 megapascal, or mostly about a megapascal or so. And how does it compare with other soft materials like rubber, skin, tissue, paper and gel. So, here is a plot of stress versus strain, and this is essentially the Hooke's law, and you can see that biological tissues of the order of a 0.1 megapascal, and then the rubber is of a megapascal, and then plastics will be of 10 to the power 9 Pascal and blah blah. So, we are actually working in this particular regime, that is rubber and gels and biological tissues or like that. So, our materials will be of this type. So, the course has got essentially three topics that we will cover. The first one is about the introduction that I am giving it today, and then where we will talk about mostly the stress strain analysis, and then we will talk about the contact mechanics. So, essentially we will talk about elastic half space, then the Hertz mechanics, and then the JKR mechanics with adhesion. We will introduce the idea of surface energy, surface tension, adhesive force, JKR contact mechanics, contact between two spherical bodies and contact between two cylindrical bodies. So, this will be the first part, and then this will be the first 10 lectures also, and then we will discuss about the contact between undulated surface. So, previously our surface of the adhesive is smooth and flat, and then we will come to this undulated surface. Rather then we will go to the rough surface. We will know that how to characterize these rough surfaces and weighting and adhesion on these rough surfaces. We will talk about briefly about the JKR contact mechanics, experiment mechanics, and the Parsons model, okay, for adhesion on these rough surfaces. Then we will talk about the deformation of confined elastic film subjected to normal load. So, the confined film, it is different from the elastic half space, the other side of the spectrum, and the adhesion of a rigid punch, okay, on a confined elastic adhesive film. So, this will be the second part. The third part will be on basically we will discuss about these peel experiments. So, where we will have the bending of thin plates, mechanics of that, and the adhesion strain measurement using this kind of flexible plate, which we call the lift off plate experiment. And we will also describe about adhesion on surface pattern adhesives, a little bit about peel experiments, and then the rate dependent adhesion, and finally we will summarize this course. So, there thus it is about 30 lectures, and I have tentatively I have shown also the number of hours that will go in each of this lecture. So, today let us start about the strain analysis. So, what is strain and how do I characterize that? So, here for example, we have a body, and this body is represented by this this shape, and there is inside the body there is a point, let us say x, y, z, and this body is subjected to some force, and therefore it deforms, and this is the deformed body. So, when you have this deformed body, we have this particular point x, y, z, it goes to let us say x star, y star and z star. So, deformation happens in the body when the body not only the position of the points they move, body that changes, but also the relative position between the different points that changes. So, that brings us to this picture. So, where let us say that we have got this vector which is p vector, and then this p vector it after deformation goes to become p star vector. So, in the unstrained state, this p vector can be represented by this psi, xi and zeta. Here it is psi star, zi star and zeta star. So, these are the components of this vector along the 3 coordinates x, y, z. So, the magnitude of this vector can be written as p square is equal to xi square, psi square and the zeta square, the magnitude square. And so, this particular vector that goes to become this p star vector. So, the difference between these two vectors is the delta p vector, and delta p vector can be written as is basically small deformation. So, the infinitesimal deformation transformation of this particular p vector that can be represented by differentiating this p square, and so this is p delta p is equal to xi delta xi, psi delta psi plus zeta delta zeta, and delta p vector, as we are saying, this is the difference between these two vectors. So, the components of this delta p vector, those are actually delta xi, delta psi and delta zeta. So, what we can think of is that delta psi, delta zeta, these are linear function of the components of the p vector. So, that is xi, psi and zeta. So, therefore, delta xi is written as a11 xi plus a12 psi plus a13 zeta. Like that, delta psi and delta zeta is also written like this as a linear function of this psi, xi and zeta. So, we can then substitute this delta xi, delta psi and delta zeta into this expression of p delta p, and we can get something like this: a11 xi square plus a22 psi square plus a33 zeta square plus a12 plus a21 into xi like that. So, this whole equation is there. So, we can get like this. And components of displacement can be written therefore little bit differently. So, here for example, delta xi is a11 xi plus a12 psi plus a13 zeta. So, that we will expand it, we can expand it as a11 xi plus half of this quantity a12 plus a21 plus half of this a13 plus a31 plus again I have added some part, so I have to subtract that part, and like this. So, like that all the components z delta xi, delta psi and delta zeta, all of this can be written like this. We can expand it like this. Why we are doing all that? We will see right now. Now, say that the length of the vector does not change because of this deformation. So, this delta p is given by this. So, this quantity has not changed because of this p becoming to p star. So, therefore, this p delta p should be equal to 0. So, if it is 0 then of course, xi, psi, zeta, these are not 0. So, therefore, these coefficients have to be 0. So, a11 A22, A33. So, A11 okay, A11 is equal to A22 is equal to A33, okay, all has to be equal to 0, and then A12 plus A21 has to be equal to 0, like that A13 plus A31 has to be equal to 0, like this. And so, therefore, this A12, okay, this is equal to minus of A21 and A13 is equal to minus of A31. So, we can write it as Aij is equal to minus of Agi. So, therefore, in the earlier expression where we have the expression for delta xi, delta psi and delta zeta, okay, we have this terms A12 plus A21, okay, those are equal to 0. So, we are left with actually these terms, okay, and where A12 is equal to minus A21. So, finally, it gives rise to these equations A12 xi plus A1 through zeta, here delta psi is equal to A21 xi plus A23 zeta, like that. So, we can substitute something like this. P is a constant, P is a coefficient. So, that represents A32 is equal to minus A23. So, we write it like this, and so what we have here is delta xi is equal to q into delta q into this zeta minus r psi. Again delta psi is equal to r into xi minus p zeta. So, you see, so here because of this transformation of this vector from p vector to p star vector, the length of the vector has not changed, but there is a finite quantity here, the delta xi, delta psi, delta zeta. So, this corresponds to actually rigid body rotation. So, whenever we have such transformations, we have to see which part is rigid body rotation. Rest of the part is actually basically corresponds to the deformation. So, here for example, from this quantity, from this equation that we wrote earlier of this delta xi, delta psi and delta zeta, okay, we have now these two parts essentially A11 xi plus a half of A12 plus A21 psi plus half of A13 plus A31 zeta, and then minus this part. So, as you can see here that if we replace here 1 with respect to 2, then this quantity, this left hand side of this dash line, okay, that does not change. So, it is basically symmetric part, and then there is this antisymmetric part. So, this antisymmetric part which is basically the rigid body rotation, okay, that does not corresponds to any deformation. So, in order when you consider the strain, we need to consider this symmetric part. So, we substitute the following notations. So, A11 is equal to Exx, A22 Eyy and A33 Ezz, and half of A32 plus A23 Eyz is equal to Ezy, because if we replace z by y, substitute, it does not change anything, and half of A12 plus A21 is equal to Exy is equal to Eyx, like that. And so, we can now write down with respect to in place of A11, A22 etc., this Exx, Eyy, Ezz, and we get this equation P delta P is equal to this equation Exx xi square plus Eyy psi square plus Ezz zeta square plus 2 Exy xi psi plus 2 Ezx xi psi zeta plus 2 Eyz psi zeta. Let us see what is the physical meaning of this particular term Eiz, that is Exx, Exy, Ez, and like that. So, let us say that we have this we have this quantity P delta P is equal to this quantity that we have, and let us try to see what are the physical what happens that if we have a vector which is defined like this psi 0 0. So, since it is psi 0 0, so in place of xi 0 0, so psi is equal to 0 and zeta is equal to 0. So, we have P delta P is equal to Exx xi square. So, therefore, this Exx, okay, will be equal to P delta B by xi square, and this since this vector is defined as xi 0 0. So, its magnitude is actually xi. So, therefore, essentially what we have is Exx is equal to delta P by P. So, what it means is that we have a vector that is along the x axis, and that has an increase and length by delta p. So, the relative increase in length of the vector, okay, that is actually this Exx, and that is called the normal strain along the x direction. Like that, we can define the normal strain along the y direction as Eyy and Ezz. Similarly, let us say that we have got a vector, two vectors here. So, p1 vector and p2 vector. So, p1 is along the y direction, a vector along y direction, and p2 is a vector along the z direction. So, here this p1 vector now becomes, let us say, p1 star vector. So, p1 star vector is given by like this, let us say, and this is, let us say, p1 star vector, and let us say p2 star vector is something like this. So, this is p2 star vector, and this p1 star vector, so it has changed. So, it was earlier 0, psi 1 and 0. So, now it is, let us say, it is delta xi 1 delta xi 1 plus psi 1 plus delta psi 1 plus delta zeta 1. Similarly, p2 star vector, that will be equal to, let us say, delta xi 2 delta psi 2 delta psi 2 plus comma here and zeta 2 plus delta zeta 2, like this. Okay. And so, the angle between these two vectors, that can be seen, angle these two vectors can be written as, this is can be pi by 2 minus, let us say, epsilon yj. So, epsilon yj is the amount of angle that these two vectors have closer, right, pi by 2. So, the angle between them, this angle is pi by 2 epsilon yj. So, the cos of this angle can be written. So, this is the cos of, so let us say cos of pi by 2 minus epsilon yz, okay, that can be written as, now this is from the vector calculations. So, that is nothing much. So, delta xi 1 delta xi 2 plus this is psi 1 plus delta psi 1 into delta psi 2 plus and here it should be comma here, it should be comma here. So, it is delta zeta 1 and into delta zeta 2 plus delta zeta 2, and here there are square root and then there are 2 square roots here. So, I will just try to fit everything over here. So, delta xi 1 square plus it is psi 1 plus delta psi 1 square plus delta zeta 1 square, and over here it is delta xi 2 square plus, we can write it. So, like that. So, finally, we have this so like that we have cos pi by 2 minus 1. So, now, so neglecting the square terms, because here as you can see we have delta xi 1 and delta xi 2. So, that is a square term. So, very small. So, those are negligible. What we have is psi 1 into delta xi 2 plus delta zeta 1 into zeta 2. So, this term here over here and this term over here, these two terms, and divided by over here you will have this psi 1 from here and zeta 2 from here. So, these two terms you have psi 1 zeta 2 here. So, essentially we have this equation over here. So, neglecting, so this we are obtaining by using only the linear terms. So, for small epsilon ij, essentially we have this delta zeta 2 by delta psi 2 by zeta 2 plus delta psi 1 by zeta 1 by psi 1. So, now what exactly it means is that you can actually write from here that this p1 is equal to 0, psi 1 0 and p2 vector was 0 0 and zeta 2. So, we substitute in this equation and we get here something like this. So, from this equation we will get here that delta psi 1 is equal to 0 here and delta zeta 1 is equal to E zy psi 1 plus P psi 1. Okay. So, we are using we are substituting for this quantity vectors with this quantities 0 psi 1 and 0 in this equation. So, we will get this equation and you divide it by the psi 1 we will get this equation. Similarly, let us say that for this particular vector P 2 vector is 0 0 and zeta 2, again I substitute over here and we get this particular equation. So, delta delta zeta 2 is equal to E y z zeta 2 delta psi 2 is equal to E y z zeta 2 minus P zeta 2. So, if I divide it we will get this expression. So, essentially you see we have got this ratio delta zeta 1 by psi 1 plus delta psi 2 by zeta 2. So, that is what we have over here, that this expression I want to get, and that is what we have gotten here, and that if I add up then we have epsilon y z is equal to this quantity is equal to epsilon u y z plus epsilon z y. So, this is equal to this. So, this define the angle through which these two vectors have rotated, and so this is called the shear strain. So, this shear strain is equal to epsilon y z plus epsilon z y, and they are symmetric, and so this is equal to 2 epsilon y z, and so this epsilon y z is equal to half of this E y z is half of epsilon y z. So, this is the definition of the shear strain. So, we have this particular equation, and we will see that so we see this P delta P is comes out to be E x x xi square plus E y y psi square plus E zeta 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 E z z zeta square plus 2 E x y psi xi 2 E x z xi psi zeta plus 2 E y z psi zeta over here. So, now this particular equation, as you can see, the left hand side defines the magnitude. So, therefore, it should be independent of the coordinate system. So, if I have, let us say that this equation here this x y z are defined in terms of this particular coordinate system. Let us say this is this. So, here let us say that this is x here, this is y, this is z here let us say, and this is y here. And now let us say that I have a different coordinate system. So, let us say this is x star and this is y star, and let us say this is z star. So, I have got a earlier coordinate system is x y z. Now, I have got let us say x star, y star and z star. So, now even if we change the coordinate system, this quantity P delta P, the meaning of that or that quantity that cannot change, that has to remain independent. So, what it means is that this we will have now instead of E x x we will have E x x x dash y E x dash x dash E x dash y dash and like that. So, we will have to like that, and then we have this instead of xi we will have xi star xi dash and psi dash and like that. So, if we have all that, then finally we will have this definition here that P delta P is equal to this, and that should also be equal to E x dash xi dash square than the other terms. So, this quantity that should remain same. So, because of the change in the coordinates from the x y z to x dash y dash and z dash, this left hand side that cannot change. So, we can actually express this xi dash y psi dash and zeta dash in terms of xi, psi and zeta. So, we can actually express that, and in order to do that we need to know that how this x dash a y dash and z dash, these are oriented with respect to this x, y and z. So, therefore, we will have here consider this the direction cosines of this x dash, y dash and z dash with respect to x, y and z. This can be given as L1 M1 N1, L2 M2 N2 and L3 M3 N3, and we can we can actually write these components of the vector in this particular form. So, we can then substitute and finally into this particular equation, and we can actually get finally that this expression. So, E x dash will be E x L1 square plus E x x M1 square like that, and E y dash z dash will be given by this. So, by this is just little algebra, and but it comes out nicely in this form. So, here we can see that we have P square E is equal to we have this E is equal to delta P by P, and delta E is the normal strain. Okay, there is a relative increase in the length of this vector with respect to this vector. So, we got that, and so therefore, this left hand side can be written as P square into E. So, E is the relative increase in the length of the vector. So, we can write it something like this. So, it is same in all the directions. So, P square is same in all the directions. So, that is a plus minus C square, and what we can see here is that say the axes are oriented now along the principal axis of the surface, then above equation simplifies to. So, let us say that we have this x, y, z. Now, we would like to orient this x, y, z in such a way that this in this matrix the diagonal elements will remain, the other elements will go. So, basically we are looking for this eigen directions or eigen values. So, if we do that, then essentially what we have to do, we have to find out the roots E1, E2, E3 of this particular determinant equation, which is this Exx minus E. So, basically we are obtaining the eigen values. So, if we do that and if we expand this, we will get this particular form minus E cube into theta E square plus this is equal to 0, and we can see this theta is given as Exx plus Eyy plus Ezz. Now, we know that for this particular matrix, okay, the summation of the diagonal elements, that is an invariant. So, therefore, Exx plus Eyy plus Ezz, that will be equal to E1 plus E2 plus E3. So, that is an invariant. So, what is that quantity? So, we can think about this particular parallelepiped in which volume V is equal to L1 into L2 into L3, and now that it has deformed. So, the deformed lengths are L1 into 1 plus E1, L2 into 1 plus E2, L3 into 1 plus E3. So, there is only the normal strains. So, if I find out the total volume of this deformed parallelepiped, so it will be L1, L2, L3 into 1 plus E1 plus E2 plus E3 plus the some higher order terms. So, therefore, we will have V into 1 plus E1 plus E2 plus E3. So, therefore, the volume strain can be written as E1 plus E2 plus E3. So, what we see is that this E1 plus E2 plus E3, which is equal to Exx plus Eyy plus Ezz, okay, is essentially the volume strain of this particular body, and so therefore, if it is an incompressible solid, this E1 plus E2 plus E3, that will be equal to 0. So, that is all I have for this lecture 1, and we will next talk about the stress analysis. Thank you.